Hi, in this lecture video, I'll be doing a quick review of thermodynamics with emphasis on organic reactions. So I'll be going over each of the variable gift-free energy, enthalpy, and entropy, and how each of these terminology are being applied here in an organic reaction to help us understand about the thermodynamics of organic reactions. So let's get started. Why do we have to consider and learn about thermodynamics of an organic reaction? As you may recall from previous video and our discussion on electron instability, in any organic reaction, the main driving force for it would then due to the stabilities of the electrons. And we know that electrons are found in the starting material and also the product. So basically, a reaction would proceed to put the electrons on the more stable substance, and assuming that would then be the product. And that is basically the driving force of a reaction, to put the electrons on the more stable substance, so that way overall it will be more favorable. And now, some reaction, in order to make it go forward, we might have to add heat to it. Whereas other reaction, instead of adding heat, we have to now cool it down by putting it in an ice bath. And some other reaction, the minute we add the reagent together and basically this got it to get started, then we do not have to continue adding more energy to it or doing more work to keep it going. But whereas other reaction, we have to continue to continuously adding energy to it. So what's going on? And so you can see that knowing and understanding about thermodynamics is really important, because this is what allows us to find the optimum reaction condition in order to carry out the reaction that we are interested in. And for that, it is important that we learn about thermodynamics, so that way we can push equilibrium in the direction that we want, depending on what we want to make. And now, whenever we mention of the word thermodynamic, we are referring to the relative stability of reactant and product at equilibrium, and how do we favor whether it is the reactant or the product, depending on what we are interested in. And as you can recall from general chemistry, when it comes down to thermodynamic, we have this very famous equation right here: delta G is equal to delta H minus T delta S. And so I just want to make sure this point right here is very clear. In this video, I will not be emphasizing on calculating any of this variable. Rather, our emphasis is on interpreting each of this terminology right here. So let's get started with the first one, the gift-free energy, or the delta G. So the gift-free energy is basically the amount of energy available to do work. And mathematically, it can be calculated by using this equation right here. So when we have the reaction, the equilibrium constant, and the temperature, and all of that variable are known, we can actually calculate the delta G of the reaction. And now, once we have compute and solve for the delta G already, if the delta G is a value that is less than 0, so in this case, it will then be negative. This has significant meaning, in which it means that this is an exergonic reaction. So let's write this down, exergonic reaction. An exergonic reaction is a reaction that releases or do work on the environment as it is happening. So therefore, this would also be called a spontaneous process. So if delta G is less than 0 or a negative value, it is an exergonic reaction where it's doing work or releasing work into the surrounding, and it is a spontaneous reaction. And by spontaneous, it basically means that it can happen on its own once it is started, and we do not have to continue input and add in, doing more work to keep it going. So once we have calculated and found that the delta G of a particular reaction is a negative value, then now we know that we do not have to continue adding energy in order to keep the reaction happening. Whereas if we were to calculate the delta G of a reaction, and now it is a value that greater than 0, or in a way, this is a positive value, then this means that this reaction is an endergonic reaction. Endergonic. And this also means that this reaction is a non-spontaneous reaction. A non-spontaneous reaction is a reaction that will require the continuous input of energy in order to keep it going. So imagine rolling a rock uphill. We keep on having to keep on rolling and adding energy in order to make it work. And this below are the potential energy diagram that can explain this. So basically, the reactant can have certain give-free energy to it, and the products can also have certain give-free energy to it. So in this case right here, the product will have lower energy than the reactant. And by lower energy here, the lower the energy, and the energy we are referring to in here is the free energy, or we can think of this as energy that associate with stability. The lower the energy, then the more the stable it will be. So in this case, the products is more stable than the reactant because have less energy. And so as the reactant is getting converted to this product right here, the difference in energy between the reactant and the product, which is this value delta G right here. So this will be the amount of energy that will be released and used and available to do work. Versus in a undergonic reaction or a non-spontaneous reaction, the product have higher energy than the reactant, or basically less stable than the reactant. And therefore, in order to make it, we have to add in this much energy right here. So yes, we will be able to make products that are less stable than reactant. It would have to require the input of energy in order to do that. And here's an example right here. The chlorination of methane reaction below has a delta G calculated to be negative 25.9 kilocal per mole at room temperature. What did this mean? And below will be the reaction. So the fact that this reaction right here has a negative delta G value, and in fact this is quite a high value, this means that this is a very spontaneous reaction. When we take methane and react this with chlorine in the presence of heat or light, all we have to do is just add some heat or light to initiate this. And once this is initiated, then it can happen on its own without any more input of energy. So it has a very large driving force that will push the reaction to completion. So that's how the delta G can tell us about the spontaneous of the reaction. So again, give free energy tell us about spontaneity of a reaction. If the reaction, if its value is negative, or reaction having a negative delta G, then it means it is a spontaneous process. Whereas if it is a positive value, it will then be a non-spontaneous process. So calculating the delta G of a particular reaction would allow us to make this determination about the reaction spontaneity. And now, let's now go over enthalpy. Whenever we hear the word enthalpy, we should be thinking of heat. And so basically, enthalpy is the amount of heat energy that has been released or absorbed in a reaction due to bond breaking and bond forming. When we perform a reaction here in organic chemistry, for certain reaction, it may release heat into the environment, where that other reaction will require the input of heat energy in order to make it happen. And again, so this is basically called the heat of reaction right here. Whether we add in them or it being released, then all of this heat associated will then be called the enthalpy of the reaction. And the enthalpy of the reaction is also referred to as the bond dissociation energy, or DBDE, or the delta H of the reaction. And the reason why that heat are involved in a reaction is because of the following. In the course of a chemical reaction, the chemical bonds are being broken, and energy is required to break a bond. And as a bond is being formed, then now energy will then be released. So due to the breaking and the forming of whatever types of particular bonds, we might be making a bond with a lot of energy and breaking a bond with less energy and so on. So basically the difference in energy due to bond formation and bond forming, that what give rise to the entropy of reaction. For an example, let's say here we have two hydrogen radicals. When these two hydrogen radicals come together to form a bond, then now this reaction right here have a delta H equal to negative 104 kilocalorie per mole. And the opposite of this process right here is when the two hydrogen molecule is dissociating, breaking to form these two hydrogen radical. So here in this case right here, the delta H of this opposite process would still be the same value, but right now the only difference would then be the sign here will be opposite. So what this means is as the bond between the two hydrogen are being produced, this is how much energy being released. And if we were to have this bond ready and now we want to break it, then it will require the same amount of energy in order to break that same amount of the hydrogen to produce these two radicals right here. And the more stable the bond, then the more energy would be needed to break it. And also the more energy would be released when it is formed. So again, very important that we remember this mnemonic right here, that energy is required to break a bond. And therefore, energy would then be released, and that same amount will be released when the bond is formed. So in the end, we can actually calculate the delta H of reaction by summing. So this sigma right here means the sum of all of the bond dissociation energy due to bond breaking. And again, when we break bond, the positive, all of the value here that we would expect to see would then be positive. And then we would then be adding the sum of energy due to all of the bond that have been formed. And in this case right here, whatever bond been formed right here, we should be expecting negative value. So by taking this value, add on to this value, and again, depending on what types of bond are being broken and which bond are formed, we have different bond energy going on. And in this case, after we add all of this together already, that will then give us the delta H of the reaction. And if the delta H of the reaction is a value that is positive or greater than 0, this basically means that the reaction is an endothermic reaction. An endothermic reaction is basically a reaction that will require the input of energy. And because the bond that we are forming are not as stable compared to the bond that we are breaking. So basically, we have to put in energy to break the more stable bond. And we're not making as stable as a bond compared to the one that we break. So that's the meaning to a positive delta H of the reaction. Versus, if the delta H of the reaction is a negative value or less than 0, it would then mean that this would be an exothermic reaction, or the reaction that releases heat into the surrounding. And this happens because the bonds that we are forming are more stable than the bond that we are breaking. So in a way, this negative sign right here will be bigger than this positive sign. So overall, the delta H of the reaction will then be a negative value. And here is the potential energy diagram to help us also understand this. So again, when we consider the entropy of the reaction, so the starting material can have certain amount of entropy to it, and also the amount of product. So here in this case right here, the product will then have less entropy compared to the starting material. So in this case right here, as the reaction is proceeding from the starting material into the product, the excess in heat energy or entropy will then be released. So this would then be an exothermic reaction. And similarly, if we were to focus on entropy again, so in this diagram, we can see here that the starting materials is having a small amount of entropy compared to the product. So as the reaction is proceed from the starting material into the product, we have to put in the difference in energy in order to make it work. So this is what an endothermic and exothermic reaction would be. So again, after we have compute and figure out what is the delta H of the reaction, it will then tell us whether the reaction is endothermic or exothermic. An endothermic reaction is again a reaction that would be requiring heat in order to keep it running. And so now we know that, okay, if we want to make these products, we have to keep on adding heat energy. Versus if the reaction has a negative delta H, meaning exothermic, then now we have to remove heat from the reaction in order to favor it. So that's the significance to why we need to be able to calculate and understand the meaning to the enthalpy of a reaction. For an example, here is the chlorination reaction of methane that we have previously seen already and calculated delta G. So here in this case right here, let's now consider delta H. So in the course of this reaction right here, as we do the analysis, we can see that we are breaking a CH bond and a CL bond. So that will be the bond that we are breaking, because we do not observe this bond on the product side. So that means as this reaction right here is happening, a CH bond and the CL bond will be broken. So therefore, bond breaking, we have to break a chlorine to chlorine bond, and that will be the bond energy of that. And we also have to break a CH bond, and this will be the bond energy for it. So in the end, this is how much energy they would take to break the two bonds in the course of this reaction. Now, on the product, we can then see that we are forming a new bond right here, CCl, and an HCl bond. So, and these are the bond energy of these two bonds. And notice that the value for them here are negative. And again, we have to put a negative sign to them rather than positive, because these are the bonds that are being formed. So it will be released, energy will be released due to this bond formation. And when we add them together, this is what it equals. And when we total, then now this reaction right here would have the following value, negative 103 kilojoule per mole. So overall, that will be the delta H of the reaction. And that basically means that this reaction would then be an exothermic reaction. So as it proceeds, heat energy would be produced. And one way that now we can favor and push equilibrium of this reaction is now by cooling it down is an ice bath to basically absorb the heat energy from the reaction. So that's one way to push the equilibrium of this reaction. And now, let's discuss entropy. As you may recall from general chemistry, entropy refers to the randomness, or the disorderness, or the freedoms of movement of a system. And a chemical reaction will be favored in the direction they have more randomness or more disorder to it. And the term entropy refers to this variable right here, delta S in the reaction. So that's what the entropy will be referring to. So the change in delta S. So basically, and this change right here would then equal to the entropy of final minus the entropy of the initial system. So if we were to now have the final on the final state on the product side, or at the end, then we have more disorderness compared to what we started out, then that is when our delta S would then be a positive value. And if this term right here is a positive term, it will then favor the spontaneity of a reaction, meaning that it favors the reactions once we get it started, we do not have to continue adding more energy in order to make it work. So it favors spontaneity when the delta S is a positive term. Versus when the delta S is a negative term, it basically means that the product has less disorderness compared to the reactant. And that is when it disfavors spontaneity of the reaction. And one thing notice for us to also point out is this terminology right here, delta S, a lot of time it is a very small term compared to the entire delta G. So yes, it can affect delta G and the reaction spontaneity. However, it has a small effect. But we can see here that it's been applied multiply with the temperature. So therefore, as the temperature is very high, this is when this delta S right here can become quite significant. So mathematically, these are how all of these terms right here are related. And again, when delta S is a positive value, it favors spontaneity, versus when it's negative, then it does not favor spontaneity. And now, let's go over some of the application of entropy. So entropy in action. First, state change. As we all know already, state change is a process that is spontaneous at higher temperature. So why is it spontaneous at high temperature? This is because of the following. As we know already, when we change from a solid into a liquid, the liquid has more movement or more disorderliness to it compared to the solid state. So going from a solid into a liquid state, the delta S will then be a positive value because the liquid has more chaos or more disorder or more entropy compared to the solid state. And similarly, when a liquid changes into the gas has even more entropy compared to the liquid. So therefore, changing from a liquid into the gas, this would also be a positive value as well. And the reverse of each of this process would then have the negative delta S. So basically, what we're looking at is in the gas state, this have the highest delta S, versus the solid state have the least delta S. So basically, this is saying that the process of changing from a solid into a liquid and a gas state will then be a spontaneous process, because again, that the gas state have the highest entropy. And this process right here would even be more spontaneous at higher temperature, because when we go back to this equation right here, if we were to now apply this and multiply this term delta S by T, then this would then become a very, very big negative value, therefore making the term delta G would even be more negative. And this is why that's the state change. It will be a spontaneous process at higher temperature when we go from a solid into the gaseous state. And second, in a chemical reaction, it may also be a process in a chemical reaction can be favored by entropy or be disfavored by entropy. For an example, so let's say here we have this reaction where we have a chlorine bonded to this carbon right here. So in this case, what we have right now will be one chemical substance. And in this process right here, the chlorine is breaking up to now produce this carbocation and this chloride. So one substance has now become two different substances. And in this case right here, the more substances that we have, then we can then see that the more disordered the system would be. So therefore, this process or this reaction or this step right here is favored by entropy. Now, it is not favored by enthalpy because we break in a bond, which require energy, right? So this step right here, it is not favored by enthalpy. However, it is being favored by entropy because on the product, there's more disorderliness due to having more substances. And another example, here's one that involves the complexity of reactant versus product. So on the reactant, we have this cyclic ring right here, where we have a bond between the atom A and atom B. If we were to now break this bond in the course of this reaction, to now break the bond between A and B, so here in this case right here, once A and B have been broken already, this molecule would now become linear, and now it can rotate, or it can have more freedom of movement, and therefore more disorderliness to it. So here in this case right here, the change from this ring structure into this linear structure right here will have a positive delta S, and this is being favored by entropy. So the breaking of rings of a ring system is being favored by entropy. And now let's do some exercise. Predict whether entropy is favored or disfavored in the following reaction. So what we have here is the breaking between a carbon and oxygen, where the electron would now be donated to the oxygen to form this following product. So what do you think? Would this product be favored or disfavored by entropy? So again, we have a ring system, and now it becomes a linear system. So in this case right here, we can see this E be in favor. So in this case, delta S will then be a positive value. And now in B, we have these carbocations and water come in to attack this to produce this product. So here in this case right here, we can see that this step right here would not be favored by entropy. So delta S would then be negative. And the reason is because we have two substances on the reactant, and now they become this one substance on the product. And now, let's now put all of this together right here. Thermodynamics. So these are the different factors and variables in this equation that we have discussed already. So let's quickly review this again. So first, the term delta G. This affects the reaction spontaneity. When the delta G is negative, then that tells us the process will then be spontaneous or exergonic, versus when it's positive, then now it would not be spontaneous. And as for delta H of the reaction, this is called enthalpy or the heat of reaction. And when it is a negative value, it means it's an exothermic process, versus when it's positive, it would then be an endothermic process. And when it comes down to entropy, that is again is the disorderness of reaction. If delta S is a positive value, this favors the spontaneity of the reaction. Versus if the delta S is a negative value, then this disfavors spontaneity. And now, lastly, temperature can also affect the reaction spontaneity as well. And now let's consider this different case right here, and let us determine whether we can see whether the process will be spontaneous or not. So if we were to now have a process where delta H is a positive value, meaning this is an endothermic process requiring heat. And now if delta S is negative, so meaning that the reaction is not becoming more but basically less disorder. So when we factor all of this together right here, then delta G, so when this is positive and this is small value right here and small negative value, they can see that overall delta G would then be positive. And if delta G is then positive, this would then be would not be a spontaneous process. Versus if we were to have a different scenario where reaction it is exothermic because delta H is negative, and now delta S is positive, so that means the system is becoming more disorder. Then when we apply all of this, then we can see that the sign of our delta G will then be negative. So this means that the process will then this reaction or this process would be spontaneous. So now, what happened if we were to now have a delta H being positive, meaning it is an endothermic reaction requiring heat, and now delta S is positive, so it is in favor in terms of entropy, but disfavored in terms of enthalpy. So what happened then? Then the answer, this reaction would then be temperature dependent. Because we can see right here, going back to this equation, if this is positive and this is also positive, then now the bigger the temperature, the more negative this term would be, and therefore the more negative delta G would be. So in this case right here, it would be temperature dependent where it is spontaneous at high temperature, because at the temperature is high, this term would then become a much bigger negative value, and therefore causing delta G to then be negative. And now another example, let's say here a delta H of a reaction, it is negative, meaning this is an exothermic reaction. And now delta S would also be a negative value as well. So in this case, this means that it not be in favor in terms of entropy. So what will happen to the reaction spontaneity then? So in this case, we would then see, so again, going back here, this is negative, so this is negative, and now this is negative. So a negative here, this would then make this term right here positive. So we want, and so because this term right here is already negative, and this term right here is positive, if we want delta G to be negative, we want this to then be a smaller term. And this is why that we want temperature to be low. So in this case right here, in this scenario, it will be temperature dependent where it is spontaneous at low temperature. And now lastly, let's also explain this question. An exothermic process or reaction always spontaneous. So this because in an exothermic reaction, it means it releases heat into the surrounding. We can see that again, this is not always spontaneous, right? Because this is exactly what we have seen previously here already. When delta H is negative, it will be a spontaneous reaction. It would be an exothermic reaction. And now whether it is spontaneous or not, it now also dependent on temperature. So we would then see the answer would no. It does not have to always be spontaneous, but now it is dependent on temperature.